This is Cosmographia, the Randall Carlson podcast. And welcome back, ladies and gentlemen. This is episode 7. Is that right?
Yes.
Episode 7, Cosmographia with Randall Carlson. We also are joined by Brad and Mike, and I'm Russ, and this is
Kyle.
my brother Kyle. He is the studio engineer, and I am the guy that asks dumb questions. So, Randall.
Don't ask him that question.
Oh, stop.
Did you, I was not going to ask that one. Did you see the two things about lunar landings? India's lander failed,
I did take note of that.
and then China's rover on the backside of the moon has seen some interesting quote unquote gel-like substance inside of a crater that they're now looking at. Gel was an interesting word. Yeah,
Moon ooze.
that's right. Moon ooze. So people were saying it might be a mistranslation, and the word might be glassy that they meant, because it was a translation from Chinese. But anyway, I thought those two things were interesting.
Mhm.
So tell us about the moon. Is what I'm trying to say.
The steering going on, I see.
Well, we were actually,
The moon. Yeah, we'll get into that someday.
yeah, we will.
Time.
But we've been working on Atlantis, so I think we should dive right back into that if you're ready.
I'm not quite ready yet, but
Uh-oh.
hold on.
Okay.
Okay, now I'm ready.
All right, sweet.
Were you talking to Edgar Casey there?
Well, no. See, now I'm channeling Metatron. It's no longer Randall Carlson speaking. This is Metatron, emissary from Atlantis.
I did not know you could
Here
channel.
we go.
Hail, Metatron. Tell us about your city. That's great.
Well, now I can actually tell you a little bit about the city, and we'll do that.
Cool.
We will actually do that. And if Metatron wants to join in, he's welcome.
All right. Yeah, but come through Mike, please. Let Randall be Randall.
Okay. Yeah, listen. Because it's I've got my hands full just channeling Randall as it is.
Yeah.
We all have our hands full channeling.
That's right.
That's enough.
Well, today is 9/9, so maybe that points us back to the moon, or a little moon teaser at least.
Oh, yeah.
9/9, yeah. And the symbolic interest or significance of the number 9. Yes. 9. Well, let's see. We find 9 in some sports, don't we?
Sure do.
Golf.
Of course we do, yeah. Golf.
Whole lot
Golf.
of baseball.
Baseball.
Of course, baseball.
Uh-huh.
Yeah, we could break down either one of those two sports because they're both very saliently symbolical once you look at them. Right?
Oh, yeah.
Deep lunar
Baseball.
connections.
Yeah, obviously lunar connections. Baseball. Okay, so how many stitches on a baseball on a official league ball? Kyle?
No idea.
72?
No, well, you're the man. You're the
144.
2/3 of the way.
Oh, I'm not supposed to guess. I'm supposed to look this up.
well. I was told at the outset of this that was your job.
Oh, okay.
Yeah. Kyle
Okay.
also doubles as the watcher. So.
Which is tough because I can't listen to people and type at the same time.
Well, I think there are now surgical procedures that could help that.
Okay.
All right, we know that number, but I guess we're getting officially Google verified here.
We're getting
Yeah.
it official.
This
We're
is
making
good.
it official.
No, this is good.
Yeah.
Didn't find it with my first query.
Well, one thing's for sure, he's not reading the stitches on a fast ball.
That's right.
Okay, well, the easy
Wow.
one. We'll let Russ answer. How many
116.
innings are there?
216? Is
216? Yeah.
that what it says?
According to an article found on www.roanoke.edu, the baseball is hand-stitched together with 216 raised stitches using 88 inches of red cotton thread.
Okay, so
There are 108 double stitches on an MLB baseball.
There you go.
There it is.
yeah, there you go. 108 double stitches. So you got 108 and 216, right?
Yeah.
And the diameter of the moon, very, very close in miles, is 2,160 miles.
Yeah.
So there's your link right there. The first link of many. So how many feet between home plate and first base, Kyle?
Oh, man. I'm going to make this take
90?
too long.
I thought it was 90 feet. Yeah, I don't know.
It is 90 feet.
Yeah,
Ah,
90
thank
feet.
you, Russ.
I used to
90
play
feet,
baseball.
And so then how many inches does that give us?
Ooh,
90 times 12. Come on, calculator.
1,440.
No,
I don't know.
no, you got to work on your math
I
skills, Ross.
can't math.
1,080.
Okay.
1,080. Now,
1,080.
here we got to pause for a minute and think about this. So you have a ratio going on here, right? The distance from home plate to the center of home plate to the center of first base. And likewise, because it's a square, right? So it's 1,080 inches from first to second, from second to third, from third back to home plate. So now you've got this distance divided into these 1,080 increments, right?
Mm-hmm.
Now you think about the ratio of the moon and the moon to the mile. You have the radius of the moon, which is a ratio. 1,080 increments defines the radius of the moon. See that? So
Yep.
yeah. And so now it's from the distance from home plate to first base, from first base to second base is going to be 2,160 inches. And the full distance around is going to be 4,320. So interestingly, just purely by coincidence, it doesn't mean a damn thing, but these are exactly the Vedic numbers, the numbers that the whole Vedic system of cosmology is built upon. And
Right.
I'm not maintaining that that's anything other than pure coincidence.
Coincidence takes planning, as Mike says.
As somebody said.
Melt
They're
and
all-
dance.
They're all processional numbers.
Yes, because the Vedic numbers are processional numbers. Yes.
Yeah.
That's the whole. Yes. So you've got the cosmological numbers of the Vedas, and just by some quirk, they end up in the sport of baseball. In terms of the dimensional relationships.
And they all add up to 9 also.
Yes.
Yeah, which is one of the peculiar, interesting properties of the number 9, that any multiple of itself
Right.
ultimately reduces back to the single digit 9.
Yeah. Yeah. In other words, all those numbers are divisible by 9.
Well, that's not what I'm saying. 2 plus 1 plus 6 is 9. 1 plus 8 is 9. 4 plus 3 plus 2 is 9.
Right. Yeah. It's like the numbers that are divisible by 9 into equal increments. You can also add in the individual digits of those numbers up to get 9.
Correct.
Yeah.
Right.
That's weird. Yeah.
Or you can eventually reduce it down to 9 by doing that.
Right. If you keep adding them up, you
Yeah.
eventually get 9. Yeah.
That process has sometimes been called Kabbalistic reduction,
Ah.
where you take a number and reduce it to a single digit. And if it's a larger number, you may have to go through several stages of reduction
Right.
to ultimately resolve it to a single digit. But yeah, so like 432, or 432 multiplied by, raised by the power of 10 times 3, 10 to the third power, you've got the number of years in the Kali Yuga, 432,000. Raised by 10 to the second power, you have 43,200, which is the number of half the number of seconds in a solar cycle, in a diurnal cycle. So if you can pinpoint, which you can, I mean, you could literally pinpoint the equinox down to a mere fraction of a second, right? But if you do that, if you can pinpoint the equinox down to less than 1 second, because it is literally, I think, like we talked about last week, just a moment in time,
Yeah.
Mhm.
which could be reduced to something almost infinitesimal, but still have just a little bit of duration. But let's say significantly less than 1 second, right? Then at that moment, there are with respect to that moment, there are 43,200 seconds of dark and 43,200 seconds of light. You see, for that moment, on that one spot where that moment would occur. See, in the diurnal rotation of the Earth on its axis. So it is built right into the astronomical, the way, and you know. So the question is again, it's purely coincidence. We don't attribute any meaning whatsoever to this, right?
Well, and the mind blower to me though is that also that I guess there's some variability, but the radius of the sun is 432,000 miles.
Yeah. So if you measure the radius of the sun in miles, you get the same number as years in the Kali Yuga, which is the basis for the system of yugas and kalpas from the Vedas. So the Dvapara Yuga, which is twice the Kali Yuga, is 864,000, right?
Yeah.
And then,
and what makes that weird is because, like, at first you could say, well, it's based on the mile, like those are all divisions of the mile, right? The sun is that many miles in its radius. But then when you look how they arrived at the mile, and you're like, wait, no, that's still based on all these geometric links between all these bodies. So,
well, see, and that's the thing. You don't know. I mean, who knows really what was the origin of the mile?
Right.
It goes back. I mean, you know, you can make assumptions about historical assumptions, but then you can go back and find what appears to be the usage of the mile, even back in the laying out of Stonehenge.
Yeah.
And we could do an analysis of that at some point too, to see how that works out.
Write that one down.
Those same numbers. See,
the other thing is that the 43,200 is the scale at which the height and the circumference, or the not circumference, the perimeter of the base of the Great Pyramid are to both the polar radius and the
equatorial radius.
Yeah.
Equatorial circumference.
Yeah.
Right. And what's interesting there is, and again, this is just purely coincidence with no significance or meaning at all. But the point is that if you were to expand the pyramid by 43, scale it up to 43,200. Yeah, you now have a square that's equivalent to the Earth's equatorial circumference and its height. And this is a hypothetical pyramid, because the real pyramid, if we're talking about, which we're referring to here, the pyramid of Cheops, has a truncated top.
Right.
So, but we can derive a perfect pyramidal geometry based upon the 51.85 degree angle of slope to base. So we can recreate a geometrically idealized pyramid, and we can then proceed to analyze that particular geometry. And when we do, we find that the internal geometry basically presents a very close approximation of the classical geometric problem of the squaring of the circle. And because it does that, what happens is we end up with the square base of the pyramid. If we use that scaling factor, 43,200 to 1, the square base of the pyramid, now if you could take that and reshape it into a circle, it would now just precisely fit the Earth's equator.
Yeah, that's wild. Pure coincidence.
Purely coincidence.
And they were obviously playing baseball,
right,
when they were doing this.
Somebody was. I think that's the point.
Yeah.
But in order to understand the scale of that baseball game, we need to go up perhaps 3 orders of magnitude. And maybe that's the point here.
No pun intended.
Yeah. Because, and we could look at the game of golf as well. I mean, we talked about that post-recording.
Yeah.
Didn't we?
True.
So at some point we'll have to come back to that. Yeah.
We will have to come back to that. Yeah. I'm going to have to have my dad down here. The stash needs to be down here for that episode, because that is going to blow his freaking mind.
He's a golfer?
Oh, yeah. He loves golf. I'm just going to stash come down. We're going to record a Randall Carlson podcast, and your mind is going to explode like all night.
Get him him that book for some holiday or birthday, that Golf in the Kingdom.
Yeah.
That'll
sure he
start
would
him
love
on
that.
his way. Yeah.
It's a good idea.
Take a note. Take a note.
Totally noted. And you know, if you're going to watch the video version of this podcast, I think there's probably a couple graphics that I can insert with that last little discussion there to get you a visual for it.
Cool. Aside from that map, that beautiful map behind you right there.
Yeah, the squaring of the circle and the
You need to put the appropriate graphics back there behind you as we're talking.
I was thinking about it. I could probably pull that off here. I'm getting better at this. I just have to duck out of the way.
And just for the information for anybody who's watching this video, on Brad, what's happening there is you may catch a glimpse now and then of Brad's doppelganger hanging out right behind him. Yeah,
What that shadow is, yeah.
He does a phenomenal job of staying precisely fixed behind Brad. You only can catch an occasional glimpse of him, but
Yeah.
he's there. He's listening in.
I was thinking it was his aura, and that aura is black.
All right. Brad is evil. That's what I thought too. Evil Brad.
I'm gonna have to make a gold green screen instead of Darth Vader screen back there.
Well, having known Brad as long as I have now, I can confirm that yes, there is a good Brad and an evil Brad. But thankfully,
Evil's
the evil
not the
Brad,
right word there.
the evil Brad is, for the most part, kind of stays out of things. So
Yeah. Evil Brad is the one that shouted at us when we were jamming out in the cabin at midnight.
yes,
That was Evil
we
Brad.
have yes. So yes, that was the evil Brad. So you guys know now what I'm talking about.
Yeah.
Uh-huh.
Scared the crap out of me.
I wasn't going to mention that event specifically, but yeah, you remember that well, don't you?
Yeah, I do. I'm never going to forget it.
You were traumatized for several days after that, as I recall.
Yeah.
Just a mere glimpse of the evil Brad.
That's right.
Only episode 7 and I'm outed. Damn.
Oh man, that we laughed about that. We still laugh about it. I had no idea that you were there. I'm jamming out, ran out around. Oh God!
Can I get any sleep around here?
Yeah. Hey, we were trying to sleep.
Trying to sleep, man.
Yeah.
I watched the whole thing from afar, laughing the entire time.
Yeah. Yeah. That's a great story.
Well, we had fun while it lasted.
Yeah.
All right, so yeah, I'm gonna be
Atlantis.
steering person here again. Yeah, so a good little teaser on some background moon info.
Mm-hmm.
9-inning
Golf.
baseball, 360 feet around the bases, etc. As we went into. So yeah, let's get back to where we were going here. Atlantisville.
Okay.
So yeah, we were looking at the Mid-Atlantic Ridge when we kind of wrapped things up last episode.
Let's get back to the Mid-Atlantic Ridge because we hadn't really covered everything that was worth covering.
Cool.
Because we're trying to put this on a solid scientific basis here. With
That's right.
Minimal speculation. Maybe at the end, once we've made our case, the scientific case, then we'll be more free to speculate. All right. So
Here we go.
We've been learning about isostasy and eustasy. So let's be clear on the difference between those two terms. Mike, or no, Russ, what's isostasy?
Excuse me. I used to know this.
It is the moving up and down of the.
Sure. It's the vertical movement of the Earth's crust
Okay, yeah.
based upon loading and unloading.
That's what I was going to say.
Compensation.
That's what you were going to say, right?
Yeah.
Okay. Okay. Well, I'll give you a second chance here. Define or just tell us what is eustasy. EUSTATICY. Eustasy.
That one I don't know. I know you've told us.
EUSTACY.
CY, yeah. I don't know what that one is.
That's what happens when you are blind. Like when you go blind,
Oh yeah, you used to see.
you used to see.
Right.
Oh, nice.
No,
Okay.
guys.
Off the rails early.
Sorry.
Okay, Eustasy is simply the rising and falling of sea level because of glacial expansion and contraction.
Oh, okay.
That's right.
If we're talking about the eustatic rise or eustatic fall of sea level, the assumption is pretty much always that that's going to be a function of the growth and the shrinkage of glaciers on land. So when the glaciers expand, sea level falls, and that would be a eustatic fall or eustatic depression of sea level. Now, when you're looking at sea level, if you're standing on the coastline and you're watching the sea move in and out, because obviously as the sea level is coming up, the shoreline of the sea is moving inland, right? And so when glaciers are growing, sea level is dropping, the shorelines are moving seaward rather than landward. Makes sense, right? So
Right.
the term we're going to use in this is the geological term. So a regression of the sea when its level is falling, and a transgression when the sea level is rising and the shoreline, the sea is now encroaching upon the land. So we've got transgression and regression. And so those are sort of interrelated terms. Eustatic rise, eustatic fall of sea level are going to cause transgression and regression, and that eustatic rise and fall of sea level is going to be a function of the growth and shrinkage of ice caps up on the continent. Got it? Now, for all time, for the rest of this incarnation, you will have that information
I think
at
so.
your disposal. I think so.
Yeah, I think
I
so.
think at this point you've got it. Okay, so all of that is relevant to what we're talking about here, whether or not a case can be made for an actual Atlantis, a proto-historical Atlantis that would have more or less conformed to what Plato actually describes in his two dialogues, Timaeus and Critias, right? That's kind of what to set out what we're attempting here. So in order to accomplish that, what we're going to do is we're going to continue to look at the narratives of the dialogues themselves to see specifically what Plato is saying. We may sometimes refer back to the original Greek that he used, the Greek terminology, just for clarification. And then we will go into looking at what actually science can be invoked or rejected that might support or refute anything specific that Plato says. What we found so far, though, is that when you have a eustatic rise or fall of sea level, you get an isostatic response in the Earth's crust. So when you depress the Earth with as the ice grows, it depresses the crust of the Earth. And when you release the ice, the Earth rebounds. Likewise, the evidence now is showing, and we begin to present some of that evidence, is that when the ice sheets are melting and the ocean level is rising, you're now increasing the loading on the ocean floor by trillions, hundreds of billions of trillions of tons of weight, literally, onto the ocean floor. You're going to get a response from the ocean floor. That's the general idea here. Now, another important idea, the geoid. The geoid is the geometry of a stable Earth, which is always fluctuating because there are constantly forces impinging upon the Earth, both internal and external, that are wanting to change the minute, the very precise shape of the geoid. But the geoid is constantly trying to maintain moving towards equilibrium. When you have the rapid onset of an ice age or the rapid termination of an ice age, and you have this rapid melting of ice and this rapid transfer of weight from the continental surface back into the ocean basins, it causes a response in the shape of the geoid. Now, because of that, when you have the vertical movements left above or below, what's going to happen is you're going to now have a region of the crust that's now out of balance with the Earth's center of mass, if you want. The tendency then is going to be for that crustal region to try to accommodate the fact that perhaps now, if it's been unloaded, let's say you're talking about a region of the Earth's crust that's being unloaded, and let's say it's at 70 to 80 degrees north latitude, and it rises by 1,500 or 2,000 feet. Well, you can see right there that that's not the distance from Earth's surface to the center of mass of the geoid anymore. You'd have to get closer to the equator for that piece of the crust to now resume equilibrium with the geoid center of mass. So what I'm getting at here is that it's likely that from the geophysical studies of the Earth would imply that there has to be accelerated lateral movement of the Earth's crust in addition to vertical movement. You see, this is kind of what I'm getting at here. So the glacial loading and unloading is going to have pretty substantial consequences to the shape of the geoid and the response of that geoid. And this response, when you have the isostatic response, it's highly probable that you're going to have a seismic response or a volcanic or both accompanying those shifts in the geoid and those redistribution of the tectonic plates. Go ahead, Mike.
Which brings us to the question I asked at the end of the last episode about, with this massive unloading of the glacial ice, the ice cap, and the loading of the water into the ocean basins, and if you posit that there was such a thing as a continent, whether you wanted to call it Atlantis or whatever, but there was some sort of landmass there, and you've got this ridge and you've got this flexion going on, right?
Yeah.
And you got some subsidence. Surely there would be other evidence around the globe of such a major shift in the.
I'm glad you asked that question, Mike. I really and truthfully am, because that's kind of where we're going with this, and we will try to get some of that in this episode, and probably can carry it over into some of the next episode to see exactly, because yes, the point is that there should be evidence. For one thing, one of the things that I would surmise is that let's say you have, as the eustatic rise of sea level presses down on the ocean floor, you're going to have an isostatic response. And that isostatic response may not be necessarily uniform. It may involve seismic movements. It may involve tremendous dislocations of along the fault line there, because we've even seen in modern earthquakes that are up, around hitting 8.0 on the Richter scale, like the Alaskan earthquake of '64. There were gigantic offsets of 30 and 40 and 50 feet, right? Now, we could be talking about here seismic events that are an order of magnitude beyond anything we've looked at in history. I mean, that, and in fact, there is some data and evidence to suggest that there were enormous seismic responses, both in, for example, the Pacific Northwest, but also in the Fennoscandian region of Northwest Europe to the rapid glacial unloading. And we can actually devote some time to looking specifically at that evidence. I don't have it right at my fingertips tonight, and that would be somewhat of a diversion. But yeah, we're definitely going to look at some stuff that would suggest that the subsidence of the ocean floor was not necessarily a gradualistic or a uniform process, but involved discrete jumps, if you will. So let's jump back to speaking of the jumps, let's jump back to 1972. What were you guys up to, Russ and Kyle, back in 1972?
Graduating college.
Waiting to be born.
Okay, you guys were waiting to be born.
Riding my big wheel.
I cannot believe I'm actually the oldest guy here.
Yeah, 72. I'm not going to get into what I was doing in 1972.
He was busy in 1972.
All I can say is that it was 1972. I was 21 years old and single, and we'll just leave it at that.
Yeah.
Was a very good year.
You were busy. Yeah, that's what I was saying.
Okay. No, 72 was actually a pretty good year for me. 72 was the year The summer of 72 was when me and my brother built those 2 geodesic domes up in northern Minnesota.
Yeah, cool.
Yeah. So that was really the start of my fascination with building and geometry. Yeah, I would say that that's very much, because prior to that, you know, even though I grew up around building and knew a little bit, I just wasn't that interested in it. But after we built those 2 geodesic domes, I got interested in it. And then when one of them came out in the national publication Shelter, which we'll pull up one day, and I got to read in there, and that was the first time. So 73, the year later, was the first year I actually learned what the golden section was and how it applied to art and architecture. But that was a direct consequence of building these 2 domes. So that 1972 was a good year for me. So anyways, this particular article came out, this paper was published in 1972, just for some perspective on this thing. And it's referring back to an article that was published by a prominent geologist named Daly back in 1925, who first was speculating about some of these ideas that are relevant to the things we've been talking about here. So I'm gonna quote here from that article here, and you'll be able to see what we are talking about here. So in a paper, largely ignored, of course, ignored in recent times, Daly in 1925 pointed out that changes in surface load over the oceans because of eustatic changes in sea level would deform the Earth. And according to Rudsky's 1889 calculations of the surface deformation of a homogeneous elastic sphere, right? Homogeneous simply means it's going to be, this is a theoretical sphere, the size of the Earth, that's going to be homogeneous, right? Meaning it's the same density and consistency throughout. Elastic meaning that it can move and respond. That it's not so rigid that it resists changing shape because of the surface loading and unloading, right? So it sounds complicated, but it's not. Calculations of the surface deformation of a homogeneous elastic sphere. So his calculation showed that the deformation would be of significant magnitude. Got it?
Got it.
So then he goes on to say that in late glacial time, the major changes in load originated from the melting of ice over Fennoscandia and North America, and the simultaneous worldwide rise in sea level from the released water. Because the surface loads involve the lateral transfer of mass, so must material be able to move laterally at depth within the asthenosphere. Now, you see what we're talking about there?
I recognize that he's saying what you were saying earlier, basically, that it can't move out and remain balanced in terms of the center of mass. Isn't that what you were talking about? It has to have some lateral motion.
Yes, but now what he's talking about is the material down even below the crust, where it becomes moltenly elastic, right? So what he's saying is that material, because the surface loads involve a lateral transfer of mass, so must the material down below be able to move laterally at depth. Okay, so in other words,
oh, I see.
Yeah, you got it. I think you got it. Yeah, you got it.
The material, the liquid material below has to be able to move around.
Right. So think about this: is the ice is building up on North America, and it's bearing down, it's pushing the plastic material outwards.
Right.
So when you're releasing weight from the ocean, you're not only the point here is that you're not only releasing the weight from above, you're now increasing the pressure from below. Because that plastic material is being squeezed to the side.
Right.
It's like squeezing a water balloon.
Yeah, it would be like squeezing a water
balloon. It bulges out, squeeze this way and bulges this way.
Yep.
Perhaps, Mike, if you could take a break and you could get a balloon and you can demonstrate that.
Demonstrate for us.
Beach ball's good. That might be easier to access.
So the point is that when the ice is forming and it's pushing down on the crust, you can imagine the molten magma underneath actually squishing out to the sides. And then when it melts and it's lifting back up, you're going to have this flow
Yes.
running in underneath.
Exactly. That's exactly it.
And the accumulation of the ice, though, was done over so many eons that the Earth had time to adjust gradually.
Right.
The unloading was so relatively sudden.
Actually, Mike, we need to qualify that because, I mean, as the token uniformitarian in the group here,
I'm not the token uniformitarian.
I didn't necessarily mean that as an insult. Remember.
All right,
yeah.
I'll play the devil's advocate. Go ahead.
Sure.
He's not going to believe anything you say now.
He never does.
Yeah.
No, where were we?
The
point I was making was that
right.
Yeah, right.
Well, yeah, the point is made and accepted. Other than the fact that I will say, actually, there's quite a bit of evidence that shows that the onset and growth of the glaciers was really, really quick.
The younger dry ice part.
Well, no, that was the late phase. That was the re-expansion of the ice sheets.
Yeah,
right.
Okay.
That was the younger dryas. But see, there was a major expansion of the ice sheets between 25 and 30,000 years ago. Right.
Oh, right. Okay.
Now, so maybe we could use this opportunity to do a couple more terms. We're talking about a continuum here, but we've got two endpoints on this continuum. We'll define an interglacial as being basically what we're in now. But now a full-on interglacial, which the Earth has actually been in multiple times, would mean that there's essentially no significant accumulated landmass of ice. Therefore, sea levels worldwide are going to be somewhere around 70 or 80 feet higher than they are now during a full-blown interglacial. But we're not talking about that. We're talking about what would probably have prevailed during the last couple of 100,000 years, right? So you've got interglacial on one side, which would be represented by now, right? And then you've got a full-blown glacial, which would have been represented by the last ice age, let's say 15 to 20,000 years ago, right? And obviously the full-blown glacial is going to correspond with the lowest subsidence of sea level, right?
Right.
Now, the climate, in turn, is having to oscillate between those two extremes, right? But those are the extremes, and all of the climatic oscillations do not go to those extremes. So you might have this climate doing this, but sometimes the climate might do this. See? So
Right.
In order to accommodate this scale of climate change, we introduce a couple new terms. And so we refer to those as a stayed and an interstayed. A stayed would be like a glacial, but not as much ice. So maybe half as much ice or 2/3 as much ice. An interstadial would mean there is some ice left, but still more than there is today. Like there may be residual ice caps, but much smaller over, say, Canada or Northwestern Europe.
Okay.
Not completely gone like they are now, because there is no perpetual, other than mountain glaciers, there's no perpetual glaciers in Canada anymore, right?
Right.
So you've got interglacial, glacial, interstayed, stayed. So here's where these terms and these concepts apply. When we go back to the previous, say, period of contracted ice, was it an interstayed or an interglacial? Well, it's pretty much agreed that to go back to the full interglacial, we go back around 105 years ago to about 120,000 years ago, which was called the Eemian period, E-E-M-I-A-N, the Eemian period. And this was a period where actually sea levels were probably 10 feet or more higher than now. And this is generally accepted as being the last full-blown interglacial period where there was no more ice on the planet than there is now. Now, the old assumption is that after this last interglacial, you had a slow return, just like Mike was talking about, a slow return of the ice sheet and growth of the ice sheet. But this may have lasted 50,000 to 100,000 years and then it began to melt away 25 or 30,000 years ago. So it was a much more protracted process back, say, from the year 1900 up to the 1950s and 1960s. But that all began to change when radiocarbon dating data came online, because one of the things that happened was that in many regions where Canada had previously been assumed to be under this unbroken mass of ice for tens of thousands of years, they were finding pollen and seeds and evidence of trees and vegetation and stuff that's dating to 30,000 years ago.
Right.
So now, this has not been done extensively enough to determine, are we talking about a full interglacial here? Probably not. But are we talking about an interstadial? Probably yes, where ice was very much constricted relative to what it became 10,000 years later, right? Now, if that's the case, there should also be a corresponding oscillation in sea levels, right? You know, let's say interglacial, sea levels way up here where they are now. Full glacial, they're down 400, maybe even 450 feet lower. Boom, boom. So interglacial, full glacial. But in between that, you've got interstade, stade, interstade, stade, because all of the oscillations in sea level are not going to be at these two extreme endpoints of that continuum. You're going to oscillate within that. So in order to address those more complex variations in climate, in glacier formation, in sea level rise and fall, that's the reason for the introduction of these additional terms. So here's the important question. When we go back 30,000 years ago, it is clear that the ice sheets over northern hemisphere were considerably constricted to what they became a short while later. And it seems that the transition from a interstade into a more full glacial occurred between 26 and 28,000 years ago. And that by 20,000 years, those ice sheets had reached their full LGM or late glacial maximum. So the implication there is that there was an enormous amount of glacial growth between, say, 26 and 28,000 years and 20,000 years ago. In fact, much faster than previously had been assumed.
That's not overnight, but that's pretty quick.
It's not overnight, but it's definitely quick. Yeah, it's definitely
it's
quick.
really fast.
In geological terms, it's that, you know.
Right.
So this is important. We're going to come back because that's an important part of the discussion. When we start talking about these great oscillations of climate, we have to come right back to this stuff that we're talking about here, because it all bears directly on the question of climate change. Because obviously, in order for the glaciers to start growing over Canada and in Northern Europe, or shrinking, you're talking about an accompanying climate change, a drastic climate change of some kind, driven by something, right? And we're not sure what, but we can speculate fairly intelligently. And one of the things that we can say with almost 100% certainty is it's not carbon dioxide driving those changes. No, I mean, that's pretty much easily demonstrable that it's not carbon dioxide. That, in fact, what we can demonstrate is that carbon dioxide fluctuations in the atmosphere are following that, because as the ocean warms, it outgasses CO2, and when it cools, it sucks the CO2 back in. It all has to do with the solubility physics of carbon dioxide. But yeah, so what we see, and again, at some point we're gonna get into that, because this is important stuff, and it's stuff that people do not know, that they need to know in order to have any kind of an informed opinion on this, you know, highly politicized matter of climate change.
Yep.
So not to get too far off, but I think these concepts are important, actually, and if we have these concepts as part of our toolbox, we can come back and talk intelligently about whether or not there could have been such a thing as Atlantis, or whether it's just complete woo. We should forget about it.
Woo's good. I don't have a problem with some woo.
No, listen.
What is the?
There's a place for woo. Just like, you know, if you're going to have a piece of cake, sometimes you spread a little frosting on there.
That's right. There you go.
But, you know, the problem is you wouldn't want to have a steady diet, 3 meals a day of frosting. And the sad thing is there's a lot of people, that's what they consume, is frosting.
Yeah.
Yeah.
Yeah. That would.
Yeah.
I'd get pretty sick, I think, after the first 2 meals of frosting.
Yes.
Yeah.
Listen, I love frosting, and I have to resist because I have a sweet tooth. But now I have finally at this stage of my life, I think, learned to resist the call of sweets.
Yep.
So
Got it.
Cake is just an excuse to have frosting.
okay, let's get back to some objective material here.
Well, I wanted to ask you. Oh, okay. You have. Never mind. Go ahead.
Go ahead. You can ask before we.
I wanted to ask you real quick. What is the, like you read this excerpt from a paper in 1972. What is the modern day take on isostasy in terms of?
Well, I mean, the basic physics was worked out way back then, and it hasn't really changed.
Okay.
I mean, what may have changed though is more empirical data showing that yes, this rapid rise and fall of sea level and isostatic adjustment of the Earth's crust. I mean, yeah, there are many more studies that have been done since then that simply bear out the fact that yes, there are these vertical movements of the Earth's crust, and we'll get into some of that right now, if that's okay with you guys.
I guess it's all right with us.
Okay, so let's go on here. This paper, by the way, was published in Quaternary Research, which is really one of my favorite journals, actually, always amongst a list of about a dozen journals that regularly addresses concepts of global change in a variety of forms. It's the R.I. Walcott is the author, and the title of the paper, this is for anybody who wants to look it up and read the paper for themselves, Past Sea Levels, Eustasy, and here Eustasy is spelled E-U-S-T-A-S-Y, Eustasy and Deformation of the Earth. Past Sea Levels, Eustasy, and Deformation of the Earth. And Kyle, do you ever use Google Scholar?
No.
Right now, while you're sitting there twiddling your thumbs, why don't you type in Google Scholar?
Okay.
I have used it. I know what you're talking about.
Yeah. They're getting more and more papers online.
Yeah, it's very useful. This is a great site, though.
Okay, I've got it here, but it is not giving an option for a PDF. No.
Okay.
You would have to go back to the journal itself. So, there was a time I actually have this paper because I began putting this information together in the 80s and early 90s before there was an internet. So when I'm talking about a paper from 1972 that I've got here, chances are I've got like a photocopy of that paper that I might have made 25, 30, 35 years ago.
Wow.
Right, but now you get more and more, you're getting access to stuff online, but a lot of stuff is behind a paywall that requires but if you use Google Scholar regularly, you'll find that there's quite a few things that just try this, Kyle. Just put in glacial isostasy. Just put that in and see what comes up. And this is, I think, useful to get into because people who are listening to this might want to do their own research. And if, students already who've done graduate level work, you're going to know all about this.
So just for new people that may still think that you're an amateur, let them know how many PDFs you've got and how many scientific papers you've read through in 40 plus years. I mean, you've got thousands is my guess.
Well, yeah, I can do a quick calculation. I usually will read typically at least one science paper on average per day. I mean, on weekends or if I'm not really busy with work, I might read 2 or 3 of them in a day. It depends. A science paper can be 1 or 2 pages long, or it can be 40 or 50 pages long, depending. But so, it wouldn't be an exaggeration to say on maybe even average 2 per day. So that would be, 700 per year, and that times 40 years would be about 29,000 papers. Now, I don't remember every one of those papers word for word, but I'll have to state right at the outset here.
You got pretty damn good recall.
Listen,
But yeah, ultimately, I did find the there's PDF access to a bunch of these articles. Like,
yeah.
you can either buy them or some of them are free.
Some
You
of
can
them are,
share the
some of them are
papers.
free.
So
Yeah,
that's really cool. Great. Thank you.
Yeah.
Google Patents is also really awesome. That's off the subject, but
hmm Okay, well let's keep going here. I hope these little asides are less distracting and more useful, people. So continue on here. So Walcott goes on to say the already complex picture of relative movements of sea level is further complicated by ground movements due to post-glacial rebound itself. The material that flows into the deglaciated area to produce uplift must come from somewhere. So we would expect a complementary depression outside the zone of uplift. So now, given the context of everything we've been discussing in the last couple of meetings here, that I think is beginning to make complete sense to me.
yep.
And why that would be relative to the question of whether or not there could have been an Atlantis, whether or not you could have had a landmass that would have risen and fallen along with eustatic changes in sea level. So he goes on to say, and then we're just about done with R.I. Walcott here. He says, if the whole mantle participated in the relaxation, these downward movements would be fairly widely spread over the Earth's surface, and therefore be of small and probably insignificant magnitude. Okay, let's do that again. If the whole mantle participated in the relaxation, think of that as you're removing these loads, right? And now the geoid is adjusting. So really, it's just like if you're sitting on a cushy chair right now, you know, the cushion is going to be under stress because of the weight of your ass, right?
That's
when
right.
you get off, right? If you were to stand up, are you sitting on a soft cushion right now?
Oh yeah.
Okay, stand up once. As you're standing up, now there's isostatic compensation.
Yeah.
Think of your ass as an ice cap, right? And think of the top of the chair as North America. And this will all begin to make sense.
Bam!
There you go.
Ice Age.
There it was. That was the rapid onset of an ice age. Just like that, boom. Okay. So let's get it. If the whole mantle participated in the relaxation, these downward movements would be fairly widely spread over the Earth's surface, and therefore be of small and probably insignificant magnitude. But if, as we suppose here, the flow is restricted to a narrow asthenospheric shell, then the downwarp will occur in a restricted zone immediately peripheral to the uplift with large and significant displacements.
All right, you're going to have to define asthenosphere.
Well, Kyle's working on that.
Yeah.
He's
I
going to
just
give
wrote
it.
it down.
Okay, and it's spelled, sometimes it's spelled A-E, but it's usually spelled A-S-T-H-E-N-O, asthenosphere. It's the region between the crust and the mantle. And it's generally a plastic zone. Which
is also the low velocity zone. Is that what they call it? The LVZ or something like that?
Well, Kyle is about to tell us.
Okay.
The asthenosphere is the highly viscous, mechanically viscous.
Viscous, yeah. You
Yes.
know what viscosity is. Okay.
Yes.
Yeah.
Highly viscous, mechanically weak, and ductilely deforming region of the upper mantle of the Earth.
Yeah. So it's what, does it give a depth there or a thickness?
It lies below the lithosphere.
Which is the sphere of rock, the crust.
Yeah. Let's see.
It's going to probably vary, 50 to 80 miles, depending. Oceanic crust is thin. Continental crust is thick.
Yeah, approximately 80 and 200 kilometers, 50 and 120 miles.
Yeah, right. There we go. Okay.
Below
so that's
the surface.
The asthenosphere. It's this viscous layer that separates the mantle from the lithosphere or the crust. And it would be in this area where these transfers, let's get where you can see that the transfer is taking place. So if the crust is moving laterally, it's moving. So crust, lithosphere, mantle down here, and here's the crust moving over the asthenosphere. Slowly in terms of continental drift, but theoretically or hypothetically, periods of accelerated motion, they're going to be accompanying the lateral transfer of mass on the Earth's surface. That's what we were referring to earlier. So his point here is that the relaxation and the stress inducement around the Earth will not be uniformly distributed, but will be concentrated in certain areas. And one of those areas would be generally very close to the region of uplift or depression. So it now makes perfect sense that as you're loading the continents with glacial ice, you're going to get an upward deformation on the bottom of the oceans, which is going to also have an accompanying complexifying effect on the level of the ocean as its bottom is rising and falling, right? Then when you have the relaxation because of the glacial unloading, you've now got loading of the ocean basins. And that, in other words, if the water may be rising over and distributed over the ocean basin uniformly, but the stresses accumulating on the ocean floor, his point here is that they will not be distributed uniformly, but will be concentrated in certain areas. So this is another important piece of information to understand the process that we're talking about here. And his conclusion is that the uplift, which would be peripheral to the area of unloading, as he says here, to use his words, would involve large and significant displacements.
And what year was this paper?
1972. So he finally then says that the physical models show that a variety of deformational effects of significant size can be expected to occur during and following the melting of the Pleistocene ice caps and the resulting eustatic rise of sea level. In Canada, the total amount of rebound at the center of uplift was between 400 and 1,000 meters. So 1,000 meters is 3,280 feet. So think about that. Think about it, a rise of up to over 3,000 feet after the glacial unloading. What would be the corresponding depression on the ocean floor along the mid-Atlantic ridge? Could it be that much?
It'd be a lot. Yeah. Yeah.
Could it be more? Well, that's very possible. Now, if you had a vertical change along the mid-Atlantic ridge of 3,000 or 4,000 feet and a rise of sea level of 400 feet, what's going to happen to any islands that are going to be along?
Yeah, they're going to be submerged very quickly.
They're going to become buttes or whatever they're called. What are they called?
Oh, the
Geos.
Geos. No, never mind. Wrong word.
Okay. Interesting stuff, isn't it?
That is, yeah, and it makes sense because the ocean floor is a thin crust. I mean, if it rose up, 3,000 something feet over the continental mass, then you can imagine that thin crust in the ocean, when that water dumps into there, that it could depress a lot farther, especially because there's also a hinge there along the ridge.
Yes. Yeah, that's exactly the point here that I want people to take away from this.
So I have a question about this. There's these areas, in the western United States where you notice mountains that look like the entire crust has been tilted, right? Mm-hmm. On one side, it's smooth and grassy, and on the other side, it's all rocky, and you can see this stratification or whatever it's called, stratification of the rock. Stratigraphy.
Yes. Stratification, that works.
Okay. Yeah, so it's like, I imagine these pieces of crust, or say at the mid-Atlantic ridge, if it was risen up, they'd be sort of pulling apart when they're risen up. And then when they're being pushed down, they're smashing together.
And what do you think might happen to upwelling magma that's in that rift, that's within that fault zone between and below, right? it could be that the pulsing of molten material laterally out over the crust that has now been well documented geomagnetically to have occurred. Right, that this material, it's almost like, think of it almost like as a wound, right? You've got a cut on your arm and you squeeze it, the blood comes out, right? But in this case, we're talking about a wound in the crust of the earth, and this material is there, and now you've got this pressure down, pressure release, pressure down, pressure release. It's very possible that process could be related to the upwelling and the outflowing of molten magma. But then once it flows out, and begins to crystallize, it preserves the geomagnetic field direction that prevailed at the time that magma is crystallized.
I was thinking you were going to talk about the granite outcrop that exists there, that you were talking about on the last podcast. It's like this leftover piece and in the middle of the mid-Atlantic ridge. So if a lot of times you'll find these granite that were basically like old volcanoes, just this big granite column that's been pushed up.
Well, yeah, there are granite. I can pull that reference up here in a minute. But yeah, there are granitic remnants right along that triple junction. In fact, that's part of the Azores Plateau.
Yeah.
Yeah, and they were saying it was a piece of the megacontinent that's left behind.
Yes.
Yeah.
Yeah. So then a couple of years later, another scientist, J. Chappell, also in quaternary research, followed up on the research of Walcott that I was just quoting from. And his conclusion was, in 1974, he uses the term hydroisostasy, which is simply talking about isostatic adjustments due to water, right, rather than presumably ice. Hydroisostasy, the concept that meltwater from Pleistocene ice caps produced loadings of ocean floors such that significant global deformation followed, recently has been examined by Walcott. The earlier qualitative assessments of hydroisostasy as an important factor in glacio-eustatism, right? We're just making up a new word here, but it's glaciers and eustasy. So glacio-eustatism are qualitatively supported by Walcott, who also demonstrated that the effects of glacio-eustatic inundation, here's the important point, will vary with location. So what that means is if it's not adjusting too much in one place, it has to be adjusting even more somewhere else. To maintain. Yeah, you got it. It. That's the idea. So,
and presumably those adjustments somewhere, it would pick somewhere else that was easy.
Path of least resistance.
That's right. Yeah.
Exactly. Okay. Well, here's a report. Now, this appeared in Nature, the prestigious British Journal of Science in 1974, the same year as the one we were just quoting from. This is deep drilling in an active geothermal area in the Azores. So in 1972, geoscientists from Dalhousie University and Lamont Doherty Geological Observatory initiated a deep drilling program into the oceanic crust. Our second borehole in 1973 was located on the island of São Miguel in the Azores. And an initial report is presented here of the 981 meters penetration of a complex sequence of subaerial and submarine lavas, pyroclastics, and volcanogenic sediments. We've defined the term subaerial, means in the atmosphere. Submarine, below the water. Pyroclastics are solid pieces of material that are part of a volcanic eruption. Like you've heard of a pyroclastic flow when you have a major, like an explosive eruption, and you have this big, almost like tidal wave of material sweeping down the sides of the mountains that are, so deadly. Yeah. That's the pyroclastic flow. Volcanogenic simply means having its genesis in a volcanic eruption, right? So what they did, they had 981 meters of core they brought up, and what they found was a complex sequence of atmospheric and submarine lavas, pyroclastic material, and volcanogenic sediments. I'll skip a couple here because it's not that directly relevant, but get right here to the crux of it. A surprising result of our experiment has been the depth at which submarine deposits were encountered. Subaerial or shallow marine conditions. Now, this is both atmospheric and shallow marine, meaning less than probably 100 or 200 feet, maybe 10, 20, 30 feet, just along the shoreline, right? So they found subaerial or shallow marine conditions are found 786 meters below present sea level and indicate substantial subsidence of the island.
Oh, yeah.
Mm-hmm. So, duh. So we're talking 2,580 feet. That's half a mile. That's half a freaking mile. Okay.
Yeah.
Which island is this?
This is São Miguel, and we'll have a map here showing. Yeah. So, man, it goes on. We're just barely getting into this, but it's interesting that we can go back to what we were talking about. I think the first couple of podcasts we did, where it was said that, from Atlantis from the geologic point of view, in light of what is known today about the ocean floors. Now, this is written in 1978. Okay. Now, just given what we already have learned in these podcasts, think about this, what they're saying here. In light of what is known today about the ocean floors, we can definitely rule out the possibility of a sunken landmass of any substantial size in the Atlantic. Or, for that matter, in any other ocean basin.
Lies.
And then, nowhere in the ocean basins is there any sign of a large mass of continental type crust, which could represent a submerged continent. Wait. Time out. I agree with that, right?
Yeah.
And from what you guys now know, you would be agreeing with that too. Yeah, there's, but let's define what we mean by large. Well, they're saying a submerged continent. Well, the smallest continent on Earth is Australia. So it's got to be at least as big as Australia or bigger to fit the definition of a continent. But nowhere was anybody ever talking about that except in the woo-woo. Plato never talked about a continent, right?
That's right.
He talked about islands.
Yep.
So then, with an Atlantic site ruled out as physically impossible, all arguments based on racial, linguistic, or other cultural similarities on both sides of the ocean, which would include the rest of Ignatius Donnelly's 13 propositions, must collapse. Either they are not real similarities at all, or they must be explained in other ways, including mere coincidence.
Yeah.
And so that was considered to be the final word on the matter in 1978. And what you see is post late 1970s, everybody starts going everywhere else and saying, oh, here I found Atlantis, it's over here.
Yeah.
Well, I found Atlantis over here, and here's why this guy is wrong, but here's why I'm right. And here's how we have to figure that Plato was mistaken about this detail or that detail. And what he really meant was this, that supports where I think Atlantis was. Now, that's not to say that some of the things that you're talking about aren't interesting, because a lot of them really are. But then to try to say, well, this is Atlantis, the question in my mind has always been, how far can we deviate from Plato's account and still legitimately call it Atlantis?
Yeah. None.
Well, at this point, at this point, we're going to have to come back to Plato because obviously we've not covered a lot of his details. But with this background and this context, once we go back and we start looking at some more of his details, I think we'll have a more insight into the whole story of Atlantis. And so, yeah, I think, did we quote from The Sunken Kingdom, the Atlantis Mystery Solved?
I don't know.
The possibility of a real Atlantis in the terms that Plato described it has long gone. That's his working premise. This came out this was a book in 1996. Yeah, he says nearly 2,400 years ago, the Greek philosopher Plato posed a riddle which has baffled scholars ever since. Was the story of the lost continent of Atlantis a complete fabrication, or did some historical reality lie behind it? The possibility of a real Atlantis in the terms that Plato described it has long gone. To which I would go, oh, really?
Yeah. He also said continent there.
Yeah, and then for all its romantic appeal, the idea of a prehistoric super civilization on an Atlantic continent is vanishingly unlikely. But again, in science, you got to define your terms. So I would ask, what the hell do you mean by a super civilization?
Yeah.
Let's define that. And then I think we can reject the use of the term continent because that was not Plato's term. I mean, Plato's terms the terms he used were well-known Greek terms for island or islands. Yeah. Yeah.
Well, I guess the only thing that's going to satisfy some people is when they dredge up an iPhone type thing embedded in rock that's 50,000 years old.
A crystal spaceship.
A crystal spaceship.
Yeah.
That would satisfy me.
Now, as is playing devil's advocate again, if I'm a geologist and I'm listening to all this and I'm saying, okay, you're taking a little bit of evidence here, a little bit of evidence there, and you're conflating this stuff, okay? What's your argument against that?
Well, I don't have an argument against that. All I can say is that I'm establishing a context in which we cannot rule out subsidence of the ocean floor, because that's ultimately what Plato is describing. He's describing islands in the mid-Atlantic, or at least west of the Pillars of Hercules, right? He doesn't specify how far, but we can come back to that. We can come back to that, and we can make some educated guesses. But in either case, he's very explicitly clear in the fact of the west of the Pillars of Hercules, which is what we now call the Straits of Gibraltar.
Right, and I think you've read some of that to me in the past, and it goes on to mention that to talk about sea levels being lower and mud flats off the coast of Africa, that kind of thing. Is that not correct?
Yeah, I mean, and we can read the relevant parts, and that's what I was saying. We need to come back now to Plato, and because what we're doing here is we're going, what does Plato say? What does modern science say? Mm-hmm. Are these two things compatible, or are they mutually contradictory? Does the science contradict the specific details that Plato provides? And do we need to take Plato completely literally? No, I'm not saying we have to take everything he says literally. But what is appearing, though, is as we go into it and we do take it, break it down by
and Plato's not talking about spaceships when they talk about when he writes about these people that were mighty warriors that fought against the Greeks. He doesn't say they flew F-16s. No. He doesn't say they came in crystal spaceships. He just said, they were mighty warriors and seafarers and
seafarers. Yes, what he is describing is a sophisticated maritime civilization centered on an island or several islands in the Atlantic Ocean west of the Pillars of Hercules. That's what he's describing.
Right, and this goes to your comments about how advanced is advanced.
Exactly.
We're not talking about again crystal spaceships. We're talking about people who sail
We're talking about people do advanced enough that they have clearly navigational
right,
skills.
Advanced navigation skills. You know?
Yes, which presumes a knowledge of astronomy, or at least enough astronomy that you can navigate.
And then some degree of higher mathematics.
Yeah.
Some degree, yes, some degree. I would agree with that, right? But no, we don't need at any point. We don't need aliens. We don't need, flying, crystal spaceships or anything. We don't need any of that. Now, that may be interesting to look into itself, because there is, some tantalizing, suggestive stuff about sophisticated technologies, but that's really a different question. And what's deficient there is really the hard evidence.
Right.
The Vedas may talk about the Vimana, the flying machine. Well, I don't know. I don't have any hard evidence for or against, but I'm open-minded enough to say, well, I would consider that if, can we make an argument based upon some kind of an evidentiary argument?
Right. But right now, just looking at the evidence that you've got.
Yes. My point is looking at what Plato.
Right. You take what Plato said, and you take, okay, let's look at the facts. Let's look at the ice caps disappeared, the sea levels rose, there was catastrophic geological action. There are indications of granitic, continent-like rock formations, and evidence of subsidence.
Yeah, that's all I'm trying to do at this point. I'm not actually making an argument for the existence of Atlantis, but I'm asking the question, when we look at Plato's relatively detailed account that he provides, he gives very specific information on the geology, on the oceanography, on the geography of it, the cultural potential of it. And, it may not be possible, and it's probably impossible at this point, to make any convincing argument for the existence of the cultural details that it provides. But step number one is to show that these notions that were put out there back in the late 70s, that this is geologically untenable. In effect, what I'm doing is I'm clearing the tabletop of all of that nonsense to show that, no, we can't dismiss the idea based upon a geological refutation, because the geology actually at this point supports the idea of subsidence of the of an island mass in the ocean.
Well,
he's dispelling the debunking, basically, is what he's doing.
I'm debunking the debunking.
Yeah. We started with Plato, and then he went to Ignatius Donnelly, and then there was the response that we went through where they said, well, we can get rid that geologically this is crap, so we can get rid of everything he said. And what Randall's been doing is showing that actually was totally wrong. Yeah. So we haven't gotten any farther than that yet.
It looks like what you were saying before, you compare what Plato said to the science of today, and can you make, is there anything that rules it out? It looks like there's nothing about science that rules it out. There's only the scientists that ruled it out.
Yeah. That's right.
A few of them in the 70s.
Yeah.
And then ever since then, really. But the science itself does not.
So far what we've seen. Okay, let's go on. We'll talk about these seamounts. We introduced seamounts last episode, right?
Yep.
We talked about seamounts, and I'm going to do a share screen here just to refresh everybody's. Let's get back to this, and there we go. Share. And actually, this may be what Brad has up, but this way we won't have to look at
Brad's doppelganger.
Brad's doppelganger, yeah. Brad, move this over to the side. Here we go. Okay, let's take a look at what we got here. Right over here, cursor is over the Pillars of Hercules, which is the Straits of Gibraltar. Inside, we have the Mediterranean. Outside, we have the Atlantic Ocean. And if we follow this dotted line here, this is the fracture zone, right? So you got the African plate down here. We've got the Eurasian plate here and the North American plate over here. And this dashed line represents the crack, if you will, between the Eurasian plate and the African plate. And it comes over here, and then it transects, it cuts in two this elevated region on the ocean floor. And it cuts right across this, and then it meets the suture zone or the fracture line between these two plates and the North American plate. And so what we have here is a triple plate junction, which obviously would be, and just, yeah, logically would be a place, a zone where you would think there would be the most flexibility in terms of isostatic adjustments, right?
Yep.
And then we've got, you can see there, these little dots. I'll pull up some better maps of them, but these are the Azores, which are actually just mountaintops that whose bases are sitting in this, if you want to call it, a microcontinent right here.
Yeah.
And then south of there, you've got these cluster of seamounts right here. And I believe, yes, there we go. So they're named, here's the Azores Islands. And then we've got, curiously named, the Atlantis Seamount here, Plato Seamount right here, Great Meteor Seamount, another interesting connection and coincidence. Make Great Meteor Seamount here, and then the Cruiser Seamount right here. So we've got these seamounts. Now let's see what we learn about seamounts. I'm going to skip a couple of things here, and here's a section looking at the Great Meteor Seamount, an east-west cross section, and you can see here the vertical scale is exaggerated to make it more prominent. It isn't quite this dramatic coming up off of the ocean floor, but that's what it looks like in profile. And here would be a bathymetric map of it, right? And the important thing to note here is the flat summit of it. We'll go through here, and here is the Atlantis Seamount. Okay, so here we have a flat top again, and we have, yeah, so here's the profile of the submerged sea map, and here's the contour intervals, the map showing the contours and the depths of these things. This is a contour interval. Okay, so this is in fathoms. So 500 fathoms would be 3,000 feet, roughly, if a fathom is 6 feet. Yeah, and here, over here in this one, you can see the depth of the top of the thing. Here's at about 400, roughly 400 fathoms. And here's the Atlantis Seamount, which got changed to the Atlantic Seamount, because you wouldn't want to have anybody thinking that, you know, that they meant to imply that this was Atlantis. Can't have that. So, okay, here we go.
How big are those seamounts? You know, you would.
Well, okay.
The tops of those plateaus. What's the width? What's the width?
Okay, right here. This is 34 degrees north, right here, and this is 34 degrees 10 minutes. So, we could figure out from that. Wouldn't be hard to do. Let's see. Let's take a look right here. Well, okay, so
I mean, there are no distance measurements here that I can tell.
Oh, there will be some in here. Let's see.
Will that distance change as you go further and further north, right? Like 10 minutes of degrees, it'll change, won't it?
Yeah, but for rough purposes, it's 20, let's see.
20 minutes, 10 minutes.
Okay, so we're looking about one mile per minute here at this latitude. So we're looking at about 10 miles here.
It's a decent sized mountain.
Yep.
Yeah.
Or plateau if it's shaved off, a plateau.
Plateau, yeah. And here they show pretty clearly on this map.
So the question is, with all these flat top mountains, what made them flat topped?
What made them flat? See, that's the question, right?
I mean, and they're all flat topped at pretty much the same height.
Right. Okay. Well, here's how you explain it. And we can actually pull up some scientific research on this. You've got mountain peak above the ocean, and now you have a highly turbulent, erosive ocean that is basically, you have to have a means of shearing off the tops of these mountains.
Yeah.
And because they're basically at the same level, that shows you that this shearing force was applied in a plane. It wasn't differential. It was in a plane. And this is what I've got up here now is a bathymetric sketch of Atlantis cruiser and Great Meteor seamounts. Great Meteor cruiser, Atlantis is over here, reproduced from The Face of the Deep by Heezen and Hollister, 1971. Bruce Heezen, by the way, was one of the founding fathers of marine geology, and tragically, he died in a submersible accident down doing research. The caption for this image reads, "Ancient sunken islands of the Eastern Atlantic." And here they are, okay, showing how the tops have been sheared off. And here's what they would have looked like before shearing.
Oh, yeah.
They would have been prominent, sharp mountain peaks rising up out of the ocean.
The trident.
Yeah, Neptune's trident.
Yeah.
Mm-hmm. So yeah, you can look up Neptune's trident and you'll find some interesting bits. So here we go. You can see very clearly the sutures. You can see the stretch marks emanating laterally from the sutures. So I'm going to stop share for the moment. Give people a chance to digest.
Well, I'm just going to throw in this little tidbit.
Please do.
I was trying to figure out how far a degree or a minute of degree change was. But what I ended up finding was the actual equatorial circumference of the planet in meters is 40,030,200.
Oh, okay.
No way.
Yes.
No.
That was how.
How is that happening? It's coincidence.
Whoa.
All right, so let's get back to some of the science here. This is from Honorez, if I'm pronouncing that right, Jay Honorez, and a group of others who published in Earth and Planetary Science Letters an article entitled Mesozoic Limestone from the Bima Offset Zone, Mid-Atlantic Ridge. Now, this is south of the Azores, but the same principle applies to this idea of vertical movement along the Mid-Atlantic Ridge, right? So in an earlier paper, Bonatti and Honorez report dredging a shallow water limestone from the summit of a transverse ridge within the offset zone of the Mid-Atlantic Ridge. The limestone was reported to contain detrital grains of quartz, orthoclase, and microcline, indicating that you don't need to know what that is for right now. Although what you need to know is that it indicates that there was a nearby source of granitic detritus, which was available during its deposition. Bonatti and Honorez have unsuccessfully attempted to explain their findings of granitic material and shallow water limestones on the basis of the present or recent geographical configuration of the equatorial Atlantic. They suggested that the limestone and its granitic mineral grains must have been deposited sometime during the Mesozoic, which of course brings us back into the age of the dinosaurs, right? We have to go back at least 66 million years.
Yeah.
Soon after the opening of the Atlantic Rift. Well and good. Within a narrow and shallow proto-Atlantic basin. If Bonatti and Honorez's interpretation is correct, it would require that the crustal block capped by the limestone was left behind during the spreading of the Atlantic floor. This possibility would have important implications. I'm going to skip over some of the really technical stuff, but they're looking at the evidence of the oxygen isotope ratios and the carbon ratios, carbon 12 and carbon 13, oxygen 16 and oxygen 18, and found that they had strongly negative values. What does that mean? Well, it means that in both cases, it's a clear indication of subaerial recrystallization. Only through the action of meteoritic water, which means rainfall, enriched in light carbon while passing through a soil zone, can the observed isotopic values be explained. So in other words, you're talking about something that's above the surface of the ocean. There's soil there, right?
Right.
Soil.
Yeah.
Right. Okay.
Dirt.
Dirt. Yes, dirt. The conclusions we derived from this study appear to confirm and extend the results obtained previously by Bonatti and Honor as follows. The components of the limestone constitute a homogeneous assemblage characteristic of a shallow water carbonate platform depositional environment. The crustal block capped by the limestone must have undergone large vertical movements, including episodes of immersion. Immersion coming out, like immersion would be going into the water, immersion coming out of the water, right? Large vertical movements where these blocks are coming up out of the ocean. If crustal spreading took place in this area, at rates of about 1.2 centimeters per year, the block capped by the limestone apparently did not move with the spreading floor. So then we're going to jump. So then we have an editorial comment on this work that I was just quoting from. This appeared in The New Scientist, 1975, volume 66, number 952, page 540. It's an editorial. Because it's an editorial, there's no optimism. Although they make no such fanciful claim from their results to have discovered the mythical mid-Atlantic landmass. Of course, they would not even consider making such a fanciful claim.
Right.
Although they make no such fanciful claim from their results as to have discovered the mythical mid-Atlantic landmass, an international group of oceanographers has now convincingly confirmed preliminary findings that a sunken block of continent lies in the middle of the friggin' Atlantic Ocean. And I think that is the first documented use of the term friggin' in the scientific literature.
Yeah. Although they make no claims that this was Atlantis, they basically found Atlantis.
4 years ago, two University of Miami workers, J. Honores and E. Bonatti, first reported the recovery of shallow water limestone fragments from the Vima fracture zone. This limestone contained minerals indicative of a nearby granitic source unlikely to occur on the ocean floor. The limestones include traces of shallow water fossils, foraminifera, green algae, bits of gastropods, and crab coprolites, implying formation in water, in one instance, less than 30 meters deep, about 100 feet. Furthermore, the limestones have been recrystallized from a high to low magnesium form of calcite, which is the thing that I was referring to earlier, that I left out the technical details. Oxygen and carbon isotope ratios prove conclusively that this process must have taken place subaerially. So, I mean, there we go. Then 2 years later, Bonatti and others, and another group of oceanographers and marine geologists published yet another paper entitled Neogene Crustal Immersion and Subsidence at the Romance Fracture Zone, Equatorial Atlantic. According to plate tectonic theory, the motions of lithospheric plates between an accretionary boundary or a spreading center and a consumptive boundary or a subduction zone, right, are essentially horizontal, taking place on the outer shell of the globe. However, some exceptions to this model appear to obtain in the vicinity of major oceanic fracture zones. Yeah, that was my thought exactly. In this paper, we present an example of vertical tectonism of a transverse crustal block located on the north side of the Romanche fracture zone. We demonstrate that the summit of this block was at or above sea level during the late Cenozoic, which geologically speaking was yesterday. So what their conclusion is that it has been suggested that the transverse morphology, Bonatti called attention to the significance of prominent east-west transverse ridges, which I will do a quick screen share here because they show up really nice on this particular map right here. Here, share, and get back to these transverse ridges.
Oh, yeah.
And that's these east-west, which I like in last episode too, basically Earth stretch marks.
Right.
Yeah. So that's what he's talking about here when he says Bonatti called attention to the significance of prominent east-west transverse ridges, some shown already by Heezen and others, which run parallel to the equatorial Atlantic fracture zones. It has been suggested that such transverse morphology associated with fracture zones could not have been produced solely by crustal spreading from axial segments of the mid-Atlantic ridge, but that vertical tectonic motions exceeding those predicted by a simple plate tectonic model must have operated. So right there, those what I'm calling the stretch marks are like the evidence. What he's calling here that they're evidence that vertical tectonic motions exceeding those predicted by a simple plate tectonic model must have operated.
Right. So those transverse ridges were made by massive vertical movements at that.
It makes sense too, because it's like when you're looking at the map, it looks flat, but really it's curved like this. So if it was going to be pushed out, it would have to crack all along that
right.
main fissure because it's actually round.
Yeah.
You know what I'm saying? Unless this is Flat Earth Society over here. It would, on a flat surface, it could rise up like this without having these cracks running this way. But because it's curved, it's got a crack in both axes.
Yeah, in order to expand outwards. And that's right.
Yeah. By Enrico Bonatti, published in 1978, also in Earth and Planetary Science Letters, is entitled Vertical Tectonism in Oceanic Fracture Zones. He says, in this paper, I will focus attention on another class of exceptions to the age depth of the oceanic crust relationship, namely on anomalies associated with large oceanic fracture zones. I will present examples from the Atlantic and Indian Oceans which suggest strong vertical tectonism to be characteristic of the large fracture zones. A qualitative estimate of vertical motions of the crust at the Romanche fracture zone was made possible in one case by the recovery of datable shallow water limestones from the summit of the transverse ridge, which is presently about 3,200 feet below sea level. On the north side of the Romanche Valley, these limestones were formed close to sea level about 5 million years ago, but subsequently have undergone episodes of immersion. In other words, they've come up and been exposed to the atmosphere.
Right. Wow.
The data discussed in this paper indicate that, get this, intense vertical tectonism of upper mantle and crustal blocks occurs along the large oceanic fracture zones. This vertical tectonism causes motions which exceed by far the small relative vertical motions of the type discussed recently. In other words, what they've discovered here in the 70s is that there has been this massive movement of the ocean floor concentrated along the oceanic fracture zones.
Yep.
Mm-hmm. So,
well, we've been going here for about an hour and a half or more, so getting up there on time, buddy.
We are, aren't we? Okay.
Yeah.
Well, I guess we'll just have to do another one.
I guess so.
I mean, I don't know what the alternative would be.
So sad.
Well, the question that Mike asked at the beginning of this is what I want to come back to. The idea that if there was a catastrophic, if this process was just not smooth and gentle and slow, but was actually a catastrophic process, there should be evidence of that.
Yeah.
So
But evidence around, not just locally, but elsewhere around the globe.
Well, yes, around the globe. But one of the things we got to bear in mind, though, is that when the Great Meltdown happened, most of the water flowing from the Laurentide ice sheet and from the Fennoscandian was going directly into the Atlantic Ocean basin. So it wouldn't be surprising to find evidence that there was the most intense seismic or isostatic activity in the Atlantic Ocean. And in the Pacific, it's going to be more uniformly distributed. But yes, what he's saying is that worldwide, along the oceanic fracture zones is where we can expect to find this intense vertical tectonism. So we basically laid the groundwork here for the idea that, yes, there could have been subsidence of a landmass, and there is a sunken landmass. We'll go ahead and say it, in the mid-Atlantic.
Yeah.
It's been referred to, the term that was invented to describe this as a microcontinent, right? And the Azores Plateau is about roughly the size of Iceland. So yeah, we'll come back and we will look for the evidence of a catastrophic episode in the Atlantic Ocean. We'll come back to that, look at that. And we'll go back to Plato's details, and with this background and this context of the scientific context, then we will go back and take a new look at some of the specifics and the details of Plato's account. Does that
Sounds
make
great
sense?
to me. Yeah. Sounds like a plan, buddy.
We got a plan, man.
Holding you to it.
So yeah, that's where we'll go with this. And then we got, to explore from there beyond, like ultimately, what was the trigger for the meltdown?
Yeah.
And again, in Plato's account, as we've talked about, I think in episode number 1, Plato actually gives us the clue right at the beginning of Timaeus with the myth of Phaeton. Remember?
Yes, that's right.
Episode 1 of the Atlantis series,
Yeah.
So we'll
which
come
is episode
back.
3.
So
Yeah.
we can actually
Correct.
use the episode, the Atlantis series as a jumping off point to exploring a lot of other interesting things, because
Right.
the meltdown itself is going to be worth looking in much greater detail, because it was a phenomenal process and most people are unaware of how fast it was and the magnitude of the events. And then ultimately we have to try to understand and come up with the trigger or triggers, as the case may be.
Yeah.
Because we're not looking at one big simple event here. We're looking at a complex series of events that maybe played out over about 3,000 years. But we're concentrated within that 3,000 year span, maybe in 3 more intense episodes. So we'll come back, and that's what we'll be going into, is the trigger. And then looking further at the worldwide consequences. And then
All right.
asking the question of how that may have affected human culture in prehistory.
All right.
Sounds like good stuff, huh?
Cosmographia to Atlantis and beyond.
I still want my crystal spaceship.
That's going to take more than an hour, and that is totally fine.
That's right. We'll build one. We'll get around to building
Mike,
them.
yeah, if you want to start researching crystal spaceships, Mike, I will try to dissuade you.
They're called comets.
Good one, Kyle.
That's what I'm here for.
That's his job.
Bad jokes.
All right, guys. Well, I guess I was ready to go for another couple hours, but yeah, we need to.
Yeah, we probably need
pull the plug.
Yeah.
Yeah,
that's right.
So track here, so we can, so I can add these some of these slides to read in the videos for people. So we're like not even to 200 yet on the slides.
Wow. Well, just want to let everybody know you guys can get a hold of us at Kosmographia1618@gmail.com. That's Kosmographia with a K. Right? That's how you spell your name?
That's right.
Also, Kosmographia, follow us on Twitter. And we have a Patreon. Brad, what's the Patreon site? Patreon.com/Kosmographia. Is that it?
We've just switched it to Randall Carlson to be very direct about it. So it's patreon.com/hello Randall Carlson. He's so excited. His name's going to be in lights.
What money? Somebody's going to send me money? Oh boy! I can't read.
Nice.
That's right.
So what we're going to do when we get the resources, we're going to invite everybody along on a big field trip. However many thousands of people, we'll all.
That'll be great.
We'll all gather up in Grand Coulee and have a good old time.
As long as we don't try to storm Area 51.
We should, though. We should. Come on.
We can make plans.
Yeah. There's very interesting geology there around Area 51.
Yeah,
so.
I'm sure there is.
Dry lake beds.
That's right. Some players.
Players, that's right. All right, we need to wrap up, but we're well on our way. What else we got to cover there at the end, Russ?
That's it. Just email us.
Thanks to everybody who has already
joined for support.
Yeah,
that's right.
Supported.
That's right.
On Patreon.
Absolutely. So some of the perk there is early access. So we're gonna let you sneak in to see the videos a little bit early once we get them ready.
Yep.
Get them ready. Depending on what level you jumped in at. So we appreciate everybody that's gotten in on to help us through Patreon.
That's right. And the audio version of the podcast should be available anywhere you get podcasts. Just search Kosmographia on iTunes or just using your podcast app and you should get it. So that's it. Also the Kosmographia YouTube channel or GeoCosmicRex. So
A1.
That's it.
Yep. Good night, Randall.
Good night, everybody.
Great, Randall.
Good night, Mike.
Yep.
Brad, Russ, and Kyle.
Ciao.
This is Kosmographia, the Randall Carlson podcast.